Okay, example 8 is all about a ladder. So they love these questions, right? Very common mechanics question. Is a ladder resting against the wall? It's like modelled as a rod. There's stuff on the ladder. It's going to be very similar to the previous question. We're going to be using moments. We're going to be using resolving horizontally and resolving vertically. But the first challenge, and this is a big challenge in itself, is labelling everything on the diagram. So I've just drawn the diagram that they've given you in the question, and I'm going to label some of the key points that they've not told us using information in the question. So the first thing the question said is the ladder AB has mass M and length 3A. So I need to know whether it's uniform or not, and if I look later in the question, it tells me that the ladder is modelled as a uniform rod. So I can put that M in the middle. So this is mg will be the force. And in terms of where I've got my A, I've got my 2A. So the length here will be 3A over 2, or 1.5A. Just call it 1.5A. It's probably slightly easier, isn't it? Okay. So then that's that. At point C, a load of mass 2m. So this becomes 2mg here. Okay, and I've already got my lengths written in there. Then we've got that it's in limiting equilibrium, so all our forces are going to balance, and it tells you that the horizontal ground is rough. So what's going on at the horizontal ground? Well, you've got contact, so that contact means there's a reaction. So this is RA, which is perpendicular to the ground. The reaction is always perpendicular, even if it's a ladder or a diagonal. And it's rough, so we've got the frictional force, right, which is mu RA. Right, that frictional force is stopping the ladder from just sliding straight down. Right, that's where the ladder wants to go. It wants to just slide this way. Over here, it says there's a smooth vertical wall, so we don't have to worry about friction. But there will be a reaction, we'll call it RB, and it will again be perpendicular from that wall. So actually with these questions it is difficult just setting it up, just working out all of the different forces that are going to be at play. Part A asks us to find the coefficient of friction between the ladder and the ground. So there are three things we can do, right? We can resolve horizontally, we can resolve vertically, and we can take moments. And it might be really unclear at this stage which of those things is actually going to be useful to us. So what we're going to do is we're just going to do them one at a time and see what equations we get out. And then once we've got the equations, we can actually see what's going on. So if we start by resolving vertically, right, we've got the RA is equal to 2mg plus mg. So RA is 3mg. Certainly going to be useful there. Right, if we resolve horizontally, we've just got only two horizontal forces. We've got this one and this one. So we've got that mu RA equals RB. So mu is RB over RA, and we know that RA is 3mg, so this is RB over 3mg. Okay, so if we can find out what RB is, then that is going to give us our value of mu. And we've done the resolving, we've resolved horizontally, we've resolved vertically, so the only other thing left for us to do is to take some moments. So if we want to get RB, it makes sense that we need to do something that's going to provide RB. And obviously there's two forces at A, so that seems a good place to eliminate by doing moments about A. Right, because now you don't have to deal with either of these two forces, the RA or the mu RA down here. So let's have a look. We've got some clockwise forces and some anti-clockwise. So imagine this is the pivot. There's two forces, the pink one's here turning us down, which is clockwise, and RB is anti-clockwise, turning us around there. Remember, moments must be perpendicular to the rod. So, none of these are perpendicular to the rod, so I'm going to draw in the perpendicular lines. to try and allow us to think about what the angles involved might be. So we're looking for those green dotted lines, and we can see the 60, so each of these is going to have a 30 here. Right, that's enough to resolve them, right, because we can think about making right angle triangles, and that would be 90, 60 and 30. Meanwhile up here you've got a Z angle in here which is 60. Alright, so then when I do my moments I can do my two clockwise ones. The first one is C, this is a distance of A, so this is A times 2mg times the angle, we're going away from the 30, sine 30, so this is 2a mg sine 30. The other one, this is clockwise, the other one is 1.5a times mg times sine 30. So we can write 1.5a mg sine 30, again clockwise. Meanwhile, the RB, the all-important RB, is going the other way. It's a distance of 3a away from A. So 3a times RB times sine 60. So this is 3a RB sine 60, and this is anti-clockwise. So because we're in limiting equilibrium, they have to balance. So we've got 2a mg sine 30 plus 1.5 a mg sine 30 equal 3a rb sine 60. Okay, so I noticed two things straight away from this. I noticed that these two are the same term, AMG sine 30, so I can add them together. And I noticed that there's an A common in all three terms. So I can divide by A, and that will cancel out this. And then I'm left with, on the left, I'll have 3.5 mg sine 30. And when I divide by 3 sine 60, that will give me my value of RB. But the problem is we've still got M that we don't know. Notice though, that's okay, because in the mu calculation I'm going to divide by M at the end anyway. So I'm going to get my answer in terms of M. So it's 3.5 times G times sine 30, all divided by 3 times sine 60, and that will tell me that I've got 6.601 M is the value of RB. So RB is dependent on M. It's going to change depending on what the masses are here and here. Just like RA. RA is dependent on M as well. But that's okay, because what that does when we go back and we put it into the mu is equal to 6.601 M divided by 3mg. M's cancel and we're left with 6.601 divided by 3 times 9.8, which gives us 0.225 to 3 significant figures. And that's part A, the coefficient friction between the ladder and the ground. Right, so lots of work, lots of very tricky question, but the idea is always the same. You can resolve horizontally and vertically, and you can take moments about a point. Right, you can take moments about multiple points if you have to. Right, but after you've drawn the diagram, that's the process. Tricky, but doable. State have used the ladder, the assumption ladder is uniform in your calculations. Right, a ladder being uniform means the centre of mass is in the middle of the ladder. Right, one of the easiest definitions you've got in the whole mechanics that if something is uniform, the centre of mass is in the middle. If it's non-uniform, the centre of mass will be at a different location to the centre.